Welcome back. This is CS 480/680 Introduction to Machine Learning, as taught at the University of Waterloo in fall 2024. And this is lecture 16, and today we're going to be talking about attention mechanisms. All right, so yeah, what is this attention? What are attention mechanisms? So far in the course, and our discussion of neural networks in particular, we've been focusing on the activities of units, in this hidden layer. We've been characterizing the activities of units in this hidden layer. And in this slide, these activations, activation Z, they were computed by applying some projection matrix W to move us from the input space of dimensionality D to some other space M, and then we applied a nonlinearity to those weighted sums. So in this case, dimensionality of input space was 4, and dimensionality of the hidden space was 5. And so these input weights were learned, but then they were fixed when it came time to make predictions. And this scheme was, loosely inspired by real biological neural networks in the brain that can trigger firing of downstream neurons that they project to. And then the weights, they roughly correspond to the number of synaptic connections made from neuron to neuron. Right. So yeah, we take some vector of inputs, apply a projection matrix, take phi here to be our nonlinearity, and that gives us the activities in that hidden layer. And this the input matrix might be some matrix of number of samples times the dimensionality. Our weight matrix, that's dimensionality D times dimensionality M to move us from D space into M space. And then in the activations can represent a matrix of the number of samples, each of which are n-dimensional. So that's been the picture of neural networks so far. Intriguingly, though, in real brains, the effect of inputs actually depend on the particular context in which the animal finds itself. So, for example, this image on the left here. These are firing patterns of neurons in the visual cortex of the mouse. So at the top here, this represents the firing pattern, specifically the spike raster when the animal is at rest. There's low firing rates during some period of time, and then a stimulus is presented onto the visual field. So there's some visual stimulus presented at a particular point in time, and what happens is that we see the firing rate increase. So if each of these vertical bars represents one spike of one neuron is being recorded, then we can see that most of these 5 neurons that we're looking at, they all started increasing. They had increased firing rate during this stimulus presentation epoch. And then when we took the stimulus away, those firing rates returned close to basal levels. And yeah, if we were to add up spikes occurring across all the neurons that we were tracking, that we would see something like this. But yeah, when animals are engaged in some kind of activity, like when they're running on a wheel, for example, the effect that this exact same stimulus has on the firing rate of neurons can change. And specifically, what we can see is that now when the animal's in a different context, when he's running, the firing rate, the increase in firing rate in response to the stimulus is increased. So we have when there's no stimulus, there's a basal level of firing rate, and then when the stimulus is presented, the neurons fire, but they fire more than they did when the animal wasn't running. Um, and the context scales firing in a multiplicative fashion is the idea here. Um, and so these the mechanisms underlying this shift are actually closely related to directing attention, specifically the expansion of pupils, the expansion of your pupils in response to different behaviors that you might be engaged in. So that these mechanisms are closely related to being able to direct your attention. So for example, if you were, focused on a task like writing some Word document, the functional the functional structure of your brain would be such to support that task. You would actually be more receptive to input to task associated inputs rather than inputs associated with the world around you. So you would be actively suppressing. Uh, it would be more difficult for those inputs to be able to uh, impact that state that you're in. But if something unexpected were to happen, like a friend calling out to you, then this would cause your attention to shift to that person. And so there's actually a link between the mechanisms of expansion of pupils and this redirection of attention to an unexpected stimulus. We don't need to worry about those details for today. But the key point is that this seems like a really powerful and flexible property of being able to redirect your attention in a dynamic way. And so is there a way to mimic this kind of behavior in neural networks? And so the way I guess the way that we're going to talk about this today is by making the weights themselves depend on the inputs. And so yeah, now whereas our weight matrix in the past, these were fixed weights, they were learned from training data. We're now going to consider a new class of models where the weights themselves are derived from the particular input that we have. And so now the activities in the hidden layer, there's still going to be a weighted sum, or some nonlinear function of a weighted sum of the input features. But now what those weights are in turn determined by the inputs that we're in. And so this new class, this more general case that we're considering now is going to allow us to do some really interesting things. And so one type of behavior that we might see is something like gain modulation. So depending on the context that we're in, yeah, for example, in one context, a particular input might cause the output of the neuron or the activation to follow some curve. But then in another context, in a slightly different setting, the same input might cause a different activation. And so this more general class of functions that we're after right now. Highly relevant application of what we're calling this attention mechanism for machine translation models, as we discussed last class in our lecture on current neural networks. So yeah, to bring this back to the French-English translation example, it's really important to be able to direct your attention only to those words that you need to in order to effectively do the translation. And so in some case, so for example, if you had an input sequence that was so many words long, you don't need access to every single word in order to translate one word. So for example, December, for example, you don't need the whole sequence in your memory in order to know that December can translate to December, or décembre can translate to December in English. On the other hand, though, there are some trickier situations, like in order to translate Bog de l'an de mille, you need to direct your attention to this entire subsequence of words at once in order to translate that correctly to Millennium Bug in English. And so we want a flexible way to be able to figure out how to direct our attention. Do we need one word? Do we need to look at the whole sentence? Can we look at part of a sentence? So this is what we're after. So yeah, for today's lecture, we're going to start thinking about how we can apply attention to sequence tasks that we started talking about in recurrent neural networks. We're then going to get into a really interesting and I guess relevant to today's large language models of, can we get attention without these sequential processing? Is an attention-like mechanism necessarily tied to sequential processing like recurrent neural networks? And then we're gonna close out by considering some of the limitations, some of the drawbacks, and some of the ethical issues around the types of models that these mechanisms have enabled. All right, so on to this first question. How can we apply attention to sequence tasks? What's that going to get us? So yeah, I said that an important application of attention is for language translation. And recurrent neural networks were once the go-to tool for handling that kind of tasks, handling that kind of task. And I didn't get too much into the architectures of, or the specific architectures of recurrent neural network that were most useful for machine translation. But at one point the state of the art were based on something called the encoder decoder architecture. And this essentially transformed one sequence to another by learning a mapping between them. But how it works is that the encoder takes an input sequence and processes it through an RNN step by step to produce a fixed length context vector. So this is this C node here. This context vector is essentially the final hidden state of the encoder. So it acts like a summary of the entire input sequence to try to capture its meaning in a condensed form. And so then the decoder, it takes this context vector as input and uses it to generate the output sequence and does this one word at a time. And so the context vector is the only information that the decoder has about the this is the the context vector is the only information that the decoder has about the input sentence, and so it's pretty crucial element to bridge the gap between two languages. So this diagram here, I guess illustrates the particular process for the case of English to French translation example. So each English word is going to get processed by the encoder side, and that produces that fixed length context vector that's then passed to the decoder, which generates the word, generates the sentence one word at a time. And so yeah, at each step, the most likely word in French is highlighted in green. And then fed into the next step of the decoder to inform the next word prediction. This architecture allowed for flexibility in sequence lengths. So the input sequence doesn't have to match the output sequence in length because it's we get this compressed kind of summary representation in the context vector C. And that's pretty crucial for tasks like machine, for language translation, where sentence structure and word orders could vary between languages. so yeah, for a long time, the encoder decoder architecture was pretty crucial for language translation. But it had a critical limitation, and that is because it relied on this fixed dimensional hidden state. Fixed dimensional context vector. Yeah, we can also call it a hidden state context vector. Uh, but yeah, this fixed dimensional context vector, that's what this whole thing relied on to capture and transfer the entire meaning of the input sequence from the encoder to the decoder, from the encoder to the decoder. And so this single vector, the idea was that this could act as a kind of sufficient statistic of the entire input so that the decoder, can use it to generate the output sequence word by word. But the problem is that when we're dealing with longer sentences, there's some nuances and specific details of the input sequence. They can get lost because the fixed size vector doesn't have enough capacity to hold all that information. And so the approach creates a kind of information bottleneck. So it restricts all the relevant details of the input, which could potentially, be a long and complicated sentence or even a paragraph into this single fixed dimensional representation. Probably okay for short sentences, but it's a problem if they're longer and more complicated. So this was an example taken from Badano, Cho, and Benjiu 2015. And so again, we're dealing with an English, in this case, an English to French translation example. And so we've got a long sentence here. So an admitting privilege is the right of a doctor to admit a patient to a hospital or medical center to carry out a diagnosis or procedure based on his status as a healthcare worker at a hospital. And so, yeah, right now we're talking about the right of a doctor to admit a patient to a hospital based on his status as a healthcare worker at a hospital. Okay, that makes sense. Healthcare workers at hospitals can admit patients. Okay, and so, but when the encoder decoder architecture was applied to this fairly long sentence, what ended up happening was uh, uh, privilege of admission is the right of a doctor to admit a patient at a hospital or a medical center for a diagnostic or to take a diagnostic test for a diagnostic procedure based on the state of his health. So they got a little bit confused at the very end there because so instead of talking about his right to admit patients based on the status of his being a healthcare worker, it became he has a right to admit patients based on the status of his own health. So that doesn't make any sense. And the authors attribute the failure to translate this longer sentence on the information bottleneck. Yeah, and I guess another way to look at the encoder decoder architecture is we've got our input sequence that's being embedded in some way that's being fed into a recurrent neural network to generate that fixed dimensional context vector or hidden state, and then the decoder generates an output sequence one word at a time. To overcome the information bottleneck in traditional sequence-to-sequence models, researchers introduced something called an attention mechanism. So whereas in a traditional model, or the traditional encoder-decoder architecture on the left here, where the encoder processes the input sequence and produces that fixed size context vector, and then passes it along to the decoder to generate its output. Attention, the encoder decoder architecture with attention, it essentially takes a step towards cutting out the middleman to try to allow the encoder and the decoder to talk to each other directly. So we're going to get into this more over the next few slides, but the key idea is that instead of compressing the input into a single state, the attention mechanism allows the allows the decoder to access each hidden state of the encoder at each time step. So yeah, if each hidden state in the encoder, represents the context and meaning associated with specific position in the input sequence, then as the decoder, is generating each word in the output, it's going to dynamically just choose which parts of the encoder's outputs, that's the sequence of hidden states, which of those to focus on. And so what we're going to see is that the attention mechanism is going to calculate a set of weights for each of the encoder's hidden states based on the current state of the decoder. And so there's going to be an aggregation step that combines the hidden states according to these weights to make a context vector that's tailored for each decoding step. So that's the key idea that we're working with. Right. So yeah. So I mentioned that we're applying these dynamically adjustable weights to the output of the encoder. So yeah, how does that work? So the very first attention mechanism was proposed by Badenow and colleagues, and they provided a clever solution to the information bottleneck problem. And yeah, so yeah, instead of using that single fixed size context vector from the encoder, Badenow's approach allowed the decoder to decide which parts of the input to focus on at each step in the output sequence. And so the attention mechanism works in three main steps. There's first computation of something called alignment scores. Then we're going to compute attention weights. And then finally, we're going to generate that context vector that's going to be fed into the decoder. So the alignment scores, they determine, so yeah, let's think about the sequence being words. So each sequence, yeah, the sequence being a sequence of words. So let's keep that example in our mind. So the alignment scores, that they essentially determine how well each word in the inputs aligns with the current word being generated in the output by the decoder. And so these are computed by some function that take both the hidden states of the encoder. So this is HI, and then the decoder's previous state, so S of t minus 1. And these states are general vectors. And so, yeah, essentially this alignment function is going to allow the model to assess the relevance of each input position relative to the current point in the output, so that it can adjust its focus dynamically. And then from there, these alignment scores E, are turned into weights by applying a softmax function. And so this normalizes the score to assign a weight alpha to each position in the input. And so the result is that each input position has a probability-like weight that reflects its relevance for generating the current output word. These weights are then used to create a context vector by combining the encoder's hidden states according to their relevance, where the relevance that we determined from the attention weights. And so this context vector that's unique to each decoding step T and acts as the decoder's dynamically kind of updated memory of the input. And so yeah, because the hidden state is a vector, the context vector is a weighted average across these vectors. So this is a context vector. So on the right hand side here, this is a visual representation of attention weights specifically. And so what this for the specific case of an English to French translation example. And so, yeah, we've got an input sequence consisting of the words, destruction of the equipment means that Syria can no longer produce new chemical weapons. And then we're translating that into French. Um, and so what we've generated here is a matrix that is number so with the number of pixels in the input sentence by the number of words in the output sentence, and then the colors represent the attention weights. So dark colors represent low attention weights, and bright colors indicate high attention weights, higher attention weights. So these might be close to 1, and these would be close to 0. And so for every word in the output sentence, we're going to compare it to every word in the input sentence, and figure out which words in the input sentence we should be paying most close attention to. And so, for example, destruction, we want to pay most close attention to destruction. That's the word that's most important for being able to do that translation. And we can see that this trend is fairly, to a first order approximation, fairly well preserved as we go through the sentence. So for example, we don't need to pay attention to anything else in order to know that destruction translates to destruction. There are a couple exceptions though. So the Syria, for example, in English, translates to la Syrie in French. And so we do need to pay attention to both of these words in order to do that translation effectively. Yeah, there's a couple other examples. My French is a bit foggy. Won't speculate on anything else. But that's the idea. So we've the context vector for destruction would be composed of a weighted sum of each of these, and destruction would be weighted most strongly, whereas everything else would be weighted close to 0. And so the context vector for destruction would be pretty close to the encoder's hidden state for destruction in that case. So Bahdanau's attention mechanism is actually just one of a larger family of attention mechanisms that we can state more generally, using a framework that was actually inspired by database structures. And so the general idea is that we have a database of key value pairs in some query queue, and then we compare the query queue to each key to compute how similar the query is with that particular key. Specifically, the attention over D is then a weighted sum of vectors indexed by I. And then the similarity score that gives us the sense of relevance or similarity for the key in answering the query. And so instead of selecting just one key, we use these similarity scores to assign a weight to each value. So the idea is that we compare the query with each key, and generate weights for each associated value, where each of these is a vector. And then these weights allow us to make a weighted combination of all the vectors to pool them into a single output vector. And so this operation is known as attention pooling, and it allows the model to pay more attention to vectors associated with the most relevant keys based on the query in question. Couple special cases that can allow us to see the flexibility here. So for example, if only one weight was set to 1 and the others were 0, you have a hard attention approach. And so that's going to basically just sift out one value, one vector. This would be similar to a traditional dictionary lookup. Another case, if you had if each weight were equal, then you would retrieve an average of all values, which might be useful for tasks where each part of the input is important. Um, but yeah, the idea is that we have these soft differentiable combinations. Yeah, generally we're working with differentiable combinations. Attention mechanisms can enable models to capture nuanced relationships and dynamically focus on the most relevant parts of the input. Um, especially useful for language tasks where the relevance of words and phrases, that really changes depending on what our context is. Um, but yeah, at its core, attention is like a soft search or a soft dictionary lookup, because given a query, which represents the information that we're trying to find, we're going to search over a database of key value pairs. Um, and yeah, where each key represents a different aspect of the input, and each value is the information that's linked to that key. All right, so I haven't gotten that specific about how those attention weights are actually computed. So yeah, we can now get into those details. So yeah, when computing attention, we need a way to measure similarity or compatibility between the query, what we're searching for, and the keys, the part of the input we're comparing against. And there's a few ways to go about this. So an early approach was called additive attention. And so there we transform the query and key vectors into a common space of the same dimensionality using weight matrices. So yeah, query and key, they in general don't need to be the same dimensionality, but we have some weight matrices to transform them into the same space. And then with additive attention, we can combine these through a nonlinear activation function like hyperbolic tangent, followed by a final weight vector to produce a single scalar form, a single scalar score. So additive attention is pretty flexible because it doesn't require you to restrict the dimensionality of the query and keys. So they could be different dimensionalities, and then you can just project them into the same space. The workhorse of the industry, though, especially nowadays, is scaled dot product attention. Is computationally simpler. So it assumes that both the queries and keys have the same dimensionality. And so here we compute the attention score by taking the dot product of the query and key vectors to give a single scalar representing their similarity. Yeah, to keep the resulting scores from becoming too large, since the dot products can grow with dimensionality. We scale the result by dividing it by the square root of the dimensions of the queries and keys to keep these attention scores stable. Finally, so when working with batches of data, we can extend these calculations by defining matrices for multiple queries, keys, and values at once. So for a batch of data, we can define matrices Q, K, and V to represent collections of queries, keys, and values respectively. So then we'd have N queries, N keys, and N values. And so the queries and keys, they need to have the same dimensionality. So so each of those vectors is dimensionality D. But then the vectors don't need to be the same dimensionality as the queries and keys. So they can be some other they can live in V space. Yeah, so yeah, we would compute the attention scores by taking the inner product between Q and the transpose of K, Q and the transpose of K, and then scaling by the square root of the dimensionality. So this would give us the attention weights, and then we would apply a softmax on this to obtain the normalized weights. And then these weights are then applied to the values in V to give us an output matrix where each element, each of the n elements is a weighted combination of the vectors or the values based on the corresponding attention scores. So yeah, this is a efficient approach to computing attention over multiple elements simultaneously to make it, practical for large scale tasks in deep learning. So our discussion so far, we've been focused on applying attention in recurrent neural networks. But one of the drawbacks of recurrent neural networks is that they're difficult to parallelize because the processing happens necessarily in a sequential fashion. And so is it possible to be able to get these kinds of contextually this contextually relevant and dynamic behavior without processing things and without having to use this sequential processing structure. And so the answer to this question came in 2018 with this groundbreaking paper called Attention is All You Need. And so what they showed is that it's possible to implement attention in a parallelizable architecture, so without sequential processing. And so we're going to spend a few minutes by really kind of digging into what this paper put forward, and because it really was quite groundbreaking and set the stage for a lot of the technologies that we've come to kind of take for granted today. Right. So how did they do it? So yeah, whereas attention in recurrent neural networks was applied to solve language translation problems where we wanted to align one sequence to another, towards developing a purely feed-forward model, feed-forward attention model, researchers focused on aligning a sequence with itself. And so what this led to was something called self-attention. And this models relationships within a single sequence, simply considering how each token relates to every other token in that sequence. And so, yeah, in this setup, each token in the input sequence is going to be able to generate its own query, its own key, and its own value vectors through learned transformations. And so these vectors enable each token to attend to all other tokens to create that rich context-aware representation that we want. So the process begins with each token's query interacting with the keys of every other token to measure the similarity. So this is done through a matrix multiplication. These are then scaled and a softmax is applied to normalize the scores into attention weights. So I've skipped over this masking step here. So this is optional. It can be applied here. It's not relevant right now, but we are going to talk about it in a few minutes. And so yeah, this part here, this gives us that's essentially the scaled dot product attention scores that we encountered a few minutes ago. So right up until this point. And then finally, we have a second matrix multiply to generate with the value vectors. And so the output of this is going to generate each token's context-aware representation by taking a weighted sum of the value vectors. So we've got our value vectors here, and then we're going to compute a weighted sum of those to give each the context-aware representation for every single token in our input sequence at the output. A couple comments here. So since self-attention computes attention scores across the whole sequence at once, this is quite a break from the sequential nature that is done in RNNs. So this can be parallelized. So this makes it we can leverage architectures like GPUs in order to get this done. But each token can directly attend to every other token. So this allows the model to capture dependencies across the entire sequence without needing it to pass information in as a step-by-step fashion as recurrent neural networks do. Um, so yeah, one thing that might be on your mind is what exactly these queries, keys, and values are and where they come from. And so in a neural network, these are learned representations of the input. So yeah, each input element is going to be transformed into a query, a key, and a vector using separate learned matrices. So for example, W sub Q, W sub K, and W sub V, respectively. And so these projections, they're going to allow the model to represent each input in terms of what it is. So that would be the value. What it should focus on in the other inputs. So that would be the key, and then what it's looking for. So that would be the query. Um, and so to compute, for example, attention for the second input element, the query is going to be compared with the keys K1, K2, all the way up to KT from all the other elements in the sequence. And so that comparison is done with the dot products to generate the alignment scores, which are here represented as omega. And then these alignment scores are going to be normalized using the softmax function to produce the attention weights. And so and those weights are going to determine how much how much focus the model should place on each value um, when generating the final output. Another question that might be on your mind is, how does self-attention compare to, what we saw with the encoder-decoder architecture and recurrent neural networks? So before we had this idea of attention, we had this, straightforward picture of the decoder being able to access the encoder's hidden states dynamically based on what the decoder was doing at that particular time step. But self-attention is a little bit more abstract because now we're talking about, tokens being able to attend to themselves and generate their own keys and queries and values. And so what does that mean and why do we need it? So let's again consider a language translation problem, but consider how it looks with self-attention. Again, English to French. The input sentence is the animal didn't cross the street because it was too tired. So one thing that we haven't that I haven't mentioned yet is that in French, every single noun has a gender assignment, so it's either the masculine or the feminine. And in order to translate this sentence effectively, one of the things we're going to have to do is recognize whether the noun to which it is referring is either masculine or feminine. So in this case, it refers to animal, and so the animal in this case would be masculine, and so in order for this translation to be done effectively, this token needs to attend all the way back here to the animal. And so in this case, we would say the animal in particular would have strong attention weights, whereas street is not so much. On the other hand, if the input sentence was the animal didn't cross the street because it was too wide, in this case, we could infer that the animal was trying to cross the street, but the street itself was too wide, and so the animal didn't want to take the risk. And so in this case, the street is what's being referred to now. And in order to correctly translate this sentence, we need to know that street is what's being referred to and correctly apply the feminine now instead of the masculine eel. And so now we want the attention to be directed to street more strongly instead of the animal in order to carry that translation out instead. Okay, so that was self-attention. But while it allows the model to capture the relationships between tokens, it's crucial to remember that the that self-attention is actually permutation invariant. And so it doesn't inherently know the order of the tokens. And so this could be problematic because in language the order of words matters for meaning. And so to tackle this, researchers proposed a clever positional encoding scheme that embeds the order information directly into the input. And how this is done is that they have this embedding matrix P, and they add to it a positional encoding matrix P. Sorry, embedding matrix X, and they add to it a positional encoding matrix P. And so the ith row of this matrix corresponds to a position I in the input sequence. And then the jth column corresponds to the jth embedding dimension. So the idea behind the construction of P is to assign a kind of unique real valued fingerprint to each position I in the sequence. And in the seminal paper, the authors used a set of sinusoidal basis functions for this. And so the frequency is different for each dimension D. And then we alternate between sine and cosine functions between consecutive dimensions. So even dimensions we use sine, and then odd dimensions we're using cosine. And then D appears is scaling the frequency term of the sine or cosine function. So each embedding dimension is going to oscillate at a different frequency. So yeah, at the top here are some examples of positional encoding values for different dimensions across positions. So the x-axis is the position, and then the y-axis is the value of the positional encoding matrix element. And then each color that corresponds to a different basis function for each embedding dimension. So what we can see is that the first few, so column 6 and 7, they're oscillating the fastest, and then higher dimensions like column 9, that's oscillating slower. And then the bottom here, this depicts the actual positional encoding matrix that would result for a situation of a sequence length of 32 and an embedding dimension of 128. And so it has this, and so what we can discern is that it has this staggered appearance because we're switching between, sine and cosine. And you can also see how the leftmost columns, they're toggling or they're oscillating the fastest. So this represents the faster frequencies, and then the higher dimensions, they're oscillating more slowly. We're gradually fading as we move from left to right. Once this positional embedding matrix is constructed, it is literally just added to the word embedding, so that this allows the model to receive both the semantic information from the embeddings as well as the positional information in P. I was a bit surprised, but this sum operation is counterintuitive, but it turns out to be efficient in terms of space. And the authors suspect that once the embeddings are learned, the model can simply adjust to something like simulate concatenation if required. The approach has a few advantages. It's flexible, can handle input sequences of arbitrary lengths, as long as they're within a predefined limit C. And then second, each position in the input sequence, that's given a distinct recognizable pattern that doesn't interfere with parallel computation. Right, so might be good to take a break at this point and make sure you understand the positional embedding computation. Um, so see if you can compute row 5 for an embedding dimension of 3, given a max sequence length of 10. So pause the video now to see if you can do that. Okay, hopefully you've taken a few minutes now to try that out on your own. Okay, so my solution, we're interested in row 5 for an embedding dimension d equals 3, and the max sequence like this is 10. For first zeroth row, j j equals 0 column, so element 5 0. We're going to compute the sine of 5 over 10 to the 2 times 0 over 3. So it's the 0th embedding dimension. 2, so this is all just 0 up here. So 10 to the 0 is 1. So we're interested in the sine of 5, which is minus 0.959. And then for the next embedding dimension, we're going to be interested in taking the cosine. So this is going to be a cosine of 5 over 10 to the 2/3. So that works out to be 0.459. That should be a cos there. And then last but not least, for position 5 2, we're going to be doing the sine of 5 over 10 to the 4 over 3. So that would be sine of 5 over 10 to the 1.33 repeating, and that works out to be roughly 0.230. So putting it all together, the row 5 in the position matrix, that's going to be negative 0.959, 0.459, and 0.23. All right, so we've seen how attention can be parallelized using self-attention and positional encoding to give the model ordering information. But with these building blocks in place, the developers, the researchers, they realized that limiting the model to just one way of calculating similarity might be too restrictive. So for example, consider this example. The cat chased the mouse down the dark alley. What notion of similarity should we focus on here? And it's not immediately clear. I've been focusing on these language translation tasks and motivating things in that way. But yeah, what notion of similarity is most meaningful for this sentence? And there's quite a few that we could consider. So we could imagine semantic similarity. So this would cause cat and mouse to attend most strongly to each other. Like a cat is a little bit like a mouse in the sense that they're both animals. They're mammals even. It's not like an alley, which is part of a city, or dark, which is an adjective. So we could focus on semantic similarity. Could also look at positional similarity. We know that the positional embedding is part of the information that the model has access to. So the cat chased the mouse down the dark alley. So this would put every consecutive word. It would cause every word to attend to most strongly to those that it appears adjacent to or close to in the sequence directly. But don't even need to stop there. What about some notion of similarity that considers the extent to which words are subjects or subjects or verbs? So this would cause cat and chase to be most strongly attended to one another. And so, yeah, as we as humans, we analyze language with each of these lenses, with each of these hats on to be able to make sense of this sentence. And so to endow machines with the same capacity, developers introduced an extension called multi-head attention. And so the idea here is that Instead of using a single attention mechanism, the model can perform attention in multiple ways simultaneously, where each one captures different types of relationships or notions of similarity between tokens in the sequence. So instead of performing one attention calculation with the full embedding dimension, we split the query's keys and values into smaller parts and apply multiple attention heads. And so each head is going to have its own set of learned projections, so it can independently look at different aspects of the relationships between tokens. And so once these individual attention functions run in parallel, they produce separate outputs, which are then concatenated and projected back into the full dimension. And so the setup allows the model to attend to information from different representational subspaces or viewpoints across the sequence to capture a richer and more diverse relationship between tokens. So going back to our example, one attention head might focus on capturing the semantic similarity between the sentence. So it might pay attention to words like cat and mouse because they're both animals and related in that meaning. Another head could focus on the positional similarity, and the third head could focus on the grammatical structure, like the subject-verb relationships. So yeah, in the sense that a single attention mechanism was kind of like one perspective or filter like we had in convolutional neural networks. Multi-head attention is like looking through multiple filters at once, where each one focuses on a type of similarity. And so this approach prevents a kind of averaging effect that you would get with if we were to just have a single head, which could blur out important nuance. And so the multi-head mechanism allows the model to capture subtle distinctions and long-range dependencies more effectively. And so these advances of self-attention, positional encoding, and multi-head attention, they've given rise to a groundbreaking neural network architecture known as the transformer. And so this diagram here illustrates the original transformer model that was introduced in the seminal paper from Vaswani. So it's got two main blocks. So the encoder is on the left, and the decoder is on the right. So it continues to mimic the encoder-decoder structure of its RNN predecessors, despite relying fundamentally on these parallelizable operations. So the encoder processes the input sequence to generate that powerful attention-based representation. So it's capable of highlighting the essential information across a wide context. And so within the encoder, so that's the encoder. And so within the encoder, there's two submodules. So we've got the multi-head self-attention layer, and then a feed-forward network. The feed-forward layer is applied pointwise, so it performs the same transformation independently at each sequence position. And then each submodule also includes a residual connection and layer normalization to make the network stable, while ensuring the outputs remain the same size throughout the encoder stack. And so in practice, each transformer stacks multiple identical layers with this same basic design. The decoder, on the other hand, this is responsible for generating the output sequence by using information from both the encoder and its own previously generated outputs. And so it's going to do this by predicting just one word at a time. So it's going to predict the first word, then it predicts the second word based on the first, and then it predicts the third word based on the first two, and so on and so forth. And so what we can see is that the decoder architecture is similar to that of the encoder. But it does include an extra layer. So the encoder has this this multi-head attention and the feed-forward network, and then the decoder also has the multi-head attention and the feed-forward network. But we've got this extra layer here. So this first multi-head attention layer in each decoder block is masked, and this ensures that each position only attends to earlier positions in the sequence. And so why do we need this? And so this masking is needed because during generation, the model does not, by definition, have access to future tokens it hasn't generated yet. But during training, the full sequence is available to the model at once. And so this is a problem because if the model could cheat, sort of, so to speak, by using future tokens to predict the current one. And so we apply a causal mask to ensure that this behavior during training restricts the attention only to tokens that it has already seen. And so, yeah, the mask is just a matrix applied during the attention computation. It effectively zeroes out future tokens by preventing any attention scores from considering tokens beyond the current position. And so, yeah, by applying the mask, the model learns to predict tokens as if it were generating them one at a time. So yeah, another way to say this is that multi-head attention preserves the auto-regressive nature of the sequence generation task, as that might be one way that you would encounter it in the literature. But yeah, on the decoder side, it then uses another multi-head attention layer, this time drawing on the encoder's output as context to allow the decoder to focus on relevant parts of the input sequence. Yeah, we can see that the transformer uses multi-head attention in three ways. So in the encoder, it performs self-attention to connect each position in the sequence with every other position. And then in the decoder, their self-attention layers handle past information only, with the causal masking preventing future positions from being accessed. And then there's the encoder-decoder attention, where the decoder queries the encoder's outputs to allow it to draw context from the input sequence. And so this setup with its combination of different attention heads and layers allows the transformer to capture both the fine-grained as well as broad relationships in the data to facilitate robust language modeling and then the sequence-to-sequence learning. Right. Yeah. Each one of these is yeah, as I mentioned, each one of these blocks is the multi-head attention, and then each one of those is doing the scaled dot product attention that we've been talking about in this lecture. So to make sure that made sense, I'd recommend pausing the lecture video at this point to see if you can link up each of the transformer blocks with these statements of the functionality. All right, so yeah, go ahead and pause, try to think it through. Okay, all right, so yeah, get started. Hopefully you've taken a minute there to work that out. Generate a rich and nuanced attention-based representation. That's the encoder's job. So that's D. Provide ordering information to the model. So that's where we add to the word embedding. So that would be the positional embedding B. Ensure attention is directed at past inputs only. So that's the job of masking that appears in the first layer of the decoder. So that's the masked multi-head attention and labeled C here. Generate the output sequence. That's the job of the decoder in general. So block E. Combines information across the sequence. That would be, where are you? find information across the sequence. That would be just A. That's self-attention there. There we go. So the transformer has really lived up to its name and being pretty transformative to the field of artificial intelligence. In a particular training paradigm has proven especially useful. And so this approach is called generative pre-training or GPT, and it involves two key phases. So there's the unsupervised pre-training and supervised fine-tuning. And so in the unsupervised pre-training phase, the model is just exposed to massive amounts of raw text, and its only goal is to learn to predict the next word. So essentially, the model learns to fill in the blank, like the quick brown fox jumped over the lazy dog, right? And so this the objective, the objective concerns the model's ability to internalize language structure, syntax, and patterns, crucially without needing labeled data. And this is essential because the amount of training data required is massive. The objective of predicting the next word is defined by the something called the language modeling loss. And so essentially, we want to find the parameters that will maximize the probability of the word at position T, given the items in the sequence up to, but not including that item. So, and we want to maximize that over all examples in our training data set. So the idea is that as the model processes, a large corpus of text, it's going to build an understanding of how words relate to each other over both short and long contexts to try to create a foundational knowledge of language. And then after pre-training, the model undergoes that supervised fine-tuning. And here it's further refined using labeled data for specific tasks. So the model is trained to predict a label, such as a sentiment or category on a given task, using a classification loss. But intriguingly, in the fine-tuning phase, the classification objective is balanced with the language modeling objective in a manner that's kind of motivated by ridge regression. And so the fine-tuning process makes the model more focused, more task-focused, to allow it to specialize in applications like text classification, sentiment analysis, or something else. The GPT paradigm has been applied to larger and larger models since its initial proposal by Radford et al. In 2018. So the first version, GPT-1, it introduced the transformer-based decoder model with around 117 million parameters. It was trained on a data set of about 600 billion words from books, approximately 40 gigs of text data. The model was capable of generating coherent responses, translating languages, even rephrasing sentences, but it was somewhat limited in its ability to handle long, complex pieces of text. It was primarily restricted to responding to shorter sentences or smaller extracts. Building on that foundation, GPT-2 was released in 2019 and had a significant increase in capacity. So it was 1.5 billion parameters. This expanded architecture allowed GPT-2 to handle larger inputs and process more extensive contexts. It was trained on data from the web, so similar amount of training data, but this time from the web. And a big difference in GPT-2 was that they did away with the supervised fine-tuning phase and just used the unsupervised the generative pre-training phase. And then in 2020, GPT-3 was released, and that had 175 billion parameters. This was trained on an even larger data set, 570 gigabytes, gathered from a wide range of sources like books, Wikipedia, things of that nature. And so this GPT-3, the massive data set combined with its size, GPT-3 was generating text with remarkable realism and depth, handled a extensive variety of prompts, and it was also at this stage where reinforcement learning with human feedback was brought into the loop. And so this was a technique that helped to align the model's responses more closely with human intent and the human value system. And so this improved its responses to make them more contextually relevant and better to better correspond with human expectations for a conversational interaction. GPT-4 is now sitting at 1.7 trillion parameters and has brought even more advanced capabilities. I haven't talked about the L1 model. Yeah, even so yeah, it continues to improve on its predecessors. We seem to still be in the rapid increase in capability phase for this technology. Scaling up these models has led to some really surprising emergent phenomena. One of the remarkable findings with GPT-2 was that it could perform tasks that it hadn't been explicitly trained on. And so this table from the GPT-2 paper demonstrates its generalization abilities by showing answers to some trivia style questions that weren't part of its training data. So, for example, when asked who wrote the book The Origin of Species, GPT-2 correctly identified Charles Darwin as the author with a confidence of 83.4%. And yeah, and so these questions weren't actually present in GPT in the web text corpus and in the training data sets that GPT-2 was trained on. But yeah, the model still provided an accurate answer with high confidence. And so this behavior has resulted in these GPT models being labeled unsupervised multitask learners. So the idea is that they were never given explicit instruction or labeled data for tasks like answering trivia questions, but the model was able to somehow leverage patterns that it learned and the extensive exposure to the text that it had to be able to make an informed guess. And so it's not perfect, but it was clearly generalizing to tasks on which it had not been explicitly trained. And then whereas GPT-2 exhibited the ability to perform tasks for which it was never explicitly trained, GPT-3 demonstrated an even more surprising behavior in that it seemed to be able to learn tasks without gradient updates. And so this capability, which we now call in-context learning, it allows GPT-3 to adapt to tasks simply based on the context provided within the prompt, rather than relying on parameter changes as we traditionally do in machine learning. And so in other words, GPT-3 can complete tasks by interpreting a natural language description or given a few examples embedded in the prompt itself. So for example, on the left side here, this is the workflow of the traditional fine-tuning approach. So the model learns English to French translation by repeated examples and a gradient update after each example. So for example, the model is given translation, given training examples like the sea otter should be l'autre de mer. A gradient update is performed. And then another example, so peppermint should be menthe poivrée. And then finally at the very end, we're interested in giving us what is the French translation for cheese. On the other hand, but GPT-3 can perform this task using in-context learning. And there's a few to be able to differentiate between types of in-context learning, we've had to get a little bit more specific and talk about zero shot, one shot, and few shot learning. So zero shot learning would mean that there's no GPT-3 is able to complete the translation task from natural language instruction alone. So this would be, translate English to French, and then, you know, uh, for this particular word, cheese. And then there's no examples given, and it's able to complete this task and correctly return fromage. And then in one-shot learning, the model is given a single example. So for example, sea otter should be l'autre de mer. Now you ask it, okay, what's cheese? It'll tell you fromage. And so, and then in few shot learning, it receives a handful of examples that establish the task's pattern before making a prediction. And so in each case, GPT-3 uses the prompt context alone to infer what it needs to do. So today there's a rich ecosystem of such transformer-based models out there. And this kind of this diagram just shows just the zoo of models that are out there. So GPT-1 and GPT-2 were precursors to those that arose later, such as GPT-4, Llama, Bard, Claude, and Anthropic. So yeah, we've got quite a few to pick from now, but I focused on the GPT models that were early in the history here. So GPT 1, 2, and 3. But a lot of others have since cropped up since GPT 3. Right, so it all sounds pretty great. We've talked a lot about what these models can do. What are some of the drawbacks of these models? So one major limitation is the amount of compute required, especially for self-attention models. So self-attention has a computational complexity of O to the n squared d, where n is the length of the input sequence and d is the dimensionality of the hidden states. So this complexity comes from the fact that each position in the sequence needs to attend to every other position. Recurrent neural networks, on the other hand, they process inputs sequentially, and so each position only connects to the next. So that's the structure means that the computational complexity of RNNs is OND squared, as they're performing a matrix vector multiplication at every step. Self-attention, though, on the other hand, is powerful in capturing relationships across the entire sequence because it's got a constant maximum path length. So mechanisms like transformers, they allow for fast and direct connections across the entire sequence. But this does come at a greater computational cost for long sequences. The computational cost of RNN scales with n, but they're less effective at capturing dependencies across distant parts of the sequence because their maximum complex the maximum path length scales with the length of the data, the length of the input sequence. So at this point, I'd like you to pause the video again to reflect briefly on some other limitations that these models might have, and let's be very general, very broad about the what I mean by limitation. So limitation, ethical concerns, reliability, things of that nature. So yeah, just take a moment, pause the video. Think about what those might be in terms of how they're trained, how they're structured, and then we'll circle back and discuss. Okay, hopefully you've taken that minute now to consider those points on your own. This was the list that I put together. So yeah, unreliable or hallucinated information. So yeah, these models generate text based on patterns in their training data. And so they can sometimes produce information that's, entirely false or fabricated. Um, you might hear the word hallucination or confabulation. And so they don't, they were never trained to really understand the facts. And so they might confidently present incorrect or misleading information. And this can be a problem in applications where accuracy is important. Poor numerical and logical reasoning. Yeah, these models they're trained primarily on natural language patterns rather than explicitly structured numerical data. So they're going to struggle with tasks that require precise arithmetic or logical reasoning or other types of structured problem solving. And so this might make them less reliable for fields that require consistent accuracy in calculations or logic. And so if I'm, of course, I have to be careful here because there's certainly variations of this model that have been fine-tuned for other types of purposes. But at least within the context of what we've talked about today and in models trained on language specifically, these are the types of language of limitations that we would expect to see. Copyright issues, lack of attribution. So yeah, many transformer models they're trained on massive data sets that were constructed by scrubbing the web, and this includes content that might have been created by writers or journalists, content creators, and so this raises copyright issues because models could really just end up regurgitating original content without proper permission and potentially violate intellectual property rights. Um, uh, I guess a lesser concern, but a concern nonetheless, is that you could have a situation where the model creates content that is similar to an original work, which might effectively be stealing the idea with and not giving any credit, even though it's not necessarily infringing on a copyright per se, but definitely poses an ethical concern around plagiarism. Subjective bias due to reinforcement learning with human in the loop. So yeah, for models that are trained in this way, our LHF, as we call it, there's a heavy reliance on human feedback to align responses with human values and expectations. This process is, it's costly and labor intensive, but can also introduce subjective biases from human raters into the model's behavior that might cause it to diverge even more strongly from its performance on numerical or logical reasoning tasks. Limited context. So yeah, transformer-based models have a fixed context window. And this limits their ability to remember information from earlier parts of long documents or conversations. And this can be an issue for applications that might require consistent reference to prior context, such as long documents or a very, very long conversation. Bias and ethical concerns. Yeah, transformer based models they really they're a reflection of the training data on which they were made, and so they're going to inherit those biases that were present in the training data that might come from a diverse and uncontrolled mix of internet sources, and so this can lead to models that might unintentionally reinforce harmful stereotypes, social biases, prejudice viewpoints. And so, yeah, efforts to mitigate this bias are ongoing, but remain a significant challenge. All right, so that brings us to the end of the lecture for today. Quick summary before we close out. So yeah, what do? We talked about the encoder-decoder architecture for an RNN. We saw that it's based on, it uses this fixed dimensional context vector in order for the encoder to talk to the decoder. And then from there, we talked about the challenges of dealing with sequential data, using RNNs, specifically, emphasized quite a bit um, on the fixed dimensional context vector, but also a bit later talked about how this creates there is the path length scales with the length of the input sequence. And we talked about the advantages of attention compared to um, as compared to RNNs. We also went over a few examples of attention functions, so we should be able to compute that for a short sequence given the queries, keys, and values. We also talked about different flavors of attention. So there was, the self-attention, massed attention, multi-head attention. So yeah, we can hopefully tell those apart by now. We also spent some time on the transformer architecture. So, we want to be able to at least label what those parts are and be able to describe, um, explain their role in the transformer architecture as a whole. Also talked about the generative pre-training paradigm in GPT-1. Yeah, and the specific objectives. So there was the unsupervised generation phase, and then the supervised fine-tuning phase. We also talked about a few applications of the transformer, so GPT-1 through GPT-4. We also talked about the in-context learning, and how that's distinct from fine-tuning involving gradient updates. And we encountered the zero shots, one shot, and few shot generation that are subtypes of in-context learning. And then finally, we spent some time on talking about both the strengths and the limitations of transformer-based attention models. And then dwelled a little bit more on the concerns involved when this is combined with generative pre-training, and using human-in-the-loop reinforcement learning. All right, I hope you got a lot out of this lecture. We'll see you back here next time when we're going to be talking about advanced optimization methods for deep neural networks.